Hi. At this point, we have a grasp on functions in terms of their formula, graph, and level curves. Moreover, we have been able to take first and higher order partial derivatives of a function. As was the case in single variable calculus, partial derivatives correspond to the slope of the graph. There is one significant drawback to partial derivatives that we have seen, however. They only give the slope in the directions parallel to the coordinate axes. For instance, in the two-variable case, they only provide the slope of the curve obtained by intersecting the graph with planes that are vertical and parallel to the x and y axes, respectively. As you can see here for the x direction and here for the y direction. In many applications, however, we also want to know about the slope in other directions. The topic of this video aims to rectify this oversight. The generalization is immediate if we stick with the previous interpretation of the partial derivatives as the slope of the curve obtained by intersection with a certain vertical plane. Instead of only considering vertical planes that are parallel to the coordinate axes, we consider vertical planes that are parallel to other vectors u in the xy plane. Again, as you can see here, we will obtain a curve in that vertical plane, and we may consider the slope of that curve. This is called the directional derivative in the direction u at the point P. While this fixes the interpretation and in theory gives a way to compute the directional derivatives, it isn't really satisfying. We want to be able to compute the directional derivative in a certain direction simply from a formula for the function. So let us recall the definition of the partial derivatives. We will stick to the two-variable case for convenience. The quotient appearing in the definition for the partial derivative with respect to x has a step size h in the denominator and the difference in function value as we take that step in the x direction in the numerator. Similarly, for the partial derivative with respect to y, we see that the quotient has the step size in the denominator and the difference in function value as we take that step in the y direction in the numerator. From this, it seems clear that what we should do to obtain the definition of the directional derivative in the u direction. Namely, we consider again the limit as the step size h goes to 0 of the quotient, which has the step size in the denominator, and the difference in function value in the u direction in the numerator. Note that it follows that the partial derivatives are directional derivatives in the direction of the standard basis vectors along the x and y axes. We need to consider only one subtlety, however. Vectors have both a direction and a length. Two vectors u1 and u2 with the same direction but different lengths will define the same vertical plane, so they should give us the same directional derivative. Let's illustrate with an example. Here we see a function f to differentiate, a direction u1 in which to differentiate, and a point ab at which to differentiate. Later on, we will not really use the limit definition to compute, however, in this simple example it will suffice. We consider indeed the limit as step size h goes to 0 of the quotient, which has the step size in the denominator, and the difference in function value in the u1 direction in the numerator. In this case, we find the value 5. Now let's try that again with the same function and the same point, but a different vector u2. As before, we can compute the limit as step size goes to 0 of the quotient with the step size in the denominator and the difference in function value in the u2 direction in the numerator. This time we find the value 10. A logical conclusion seems to be that the function is twice as steep in the u2 direction as in the u1 direction. But that makes no sense, since u1 and u2 actually point in the same direction. Indeed, u2 is just twice u1. A function cannot have two different slopes in the same direction. Clearly, the length of the vector u has an effect on the value of the limit. For this reason, we include the condition that the vector u used to define the directional derivative has unit length. In case a direction is provided by a vector which is not of unit length, we must therefore first normalize the vector in order to compute the directional derivative. Normalizing means we find a vector with the same direction but unit length. In practice, this is obtained by simply dividing the vector by its own length. So if we consider the example from before, we see that neither of the two vectors was actually a unit vector. So neither of those two limits was actually the directional derivative in the direction given by those vectors. By normalizing the vector, in other words dividing it by its length, which happens to be the square root of 5, we can obtain the actual directional derivative. Computing directional derivatives by using the definition directly is usually quite hard. Luckily, there's a useful shortcut involving the partial derivatives. As you can see on the slide, the directional derivative in the direction of the vector u is given by the sum of products of the partial derivatives with the corresponding entries of that vector u. Be careful, however, you still need that vector u to be of unit length. Before we consider an example, it might be good to also consider the definition and theorem in the context of more than two variables. Here they are. Hopefully, these generalizations are not unexpected. As an example, consider the function you see on the slide. We have learned to compute the partial derivatives. Indeed, they are as indicated on the slide, and it is clear that they do indeed correspond to the slope of the x and y directions, respectively. Now let's consider the particular point 1, 2, and consider the partial derivatives at that point. What is the slope in that point in the direction of the indicated vector u, which points to the z-axis along the line where y equals twice x? Of course, we should be careful to consider the normalized vector in that direction, obtained by dividing the previous vector minus 1 minus 2 by its length, which was square root of 5. Now we can use the formula we just learned to compute the slope, namely negative 2 times negative 1 over square root of 5 plus 4 times negative 2 over square root of 5. In short, we have computed the value of the partial derivatives in the point of interest, multiplied them with the corresponding entries of the unit vector in the direction of interest, and finally added these products together. This expression of taking the sum of a product of components of a vector has a particular name and meaning in linear algebra. It is called the dot product, or sometimes the inner product. So indeed, we can view the directional derivative as a dot product. Clearly, one of the vectors in the dot product is the vector u. But what is the other vector? In fact, the other vector is called the gradient vector. At each point in the domain, its entries are equal to the partial derivatives in that point. So the first component corresponds to the partial derivative with respect to the first variable. The second component corresponds to the partial derivative with respect to the second variable, and so on. The notation, which looks like an upside-down delta, is called a nabla. For example, for the function f given by 3xy minus x squared, we can compute as indicated on the slide that in the point 2, 1, the partial derivative in the x direction is given by negative 1, and the partial derivative in the y direction is given by 6. And so the gradient vector at that point is negative 1, 6. Indeed, now we see that the directional derivative in the direction u at the point P is given by the dot product of that vector u with the gradient vector at that point P. It turns out that the gradient vector provides a ton of information about the function. Note that since the gradient assigns a vector to each point, we can think of it as a function from Rn to Rn. In particular, this kind of function is called a vector field. Indeed, it assigns a vector to each point in the domain of the function. Here is the example from before, and since we already computed the partial derivatives, we easily find the gradient vector field by assigning to each point the vector with the partial derivative with respect to x as the first component, and the partial derivative with respect to y as the second component. As you can see by taking the dot product with unit length vectors, we can easily determine the directional derivatives in those directions. For instance, if we take the function we have been considering and the unit vector with first component 3 over 5 and second component 4 over 5, then we see straightforwardly that the directional derivative in the point 1, 2 is 24 over 5. Before we move on to explore the different properties of the gradient vector, let's make sure to practice computing and interpreting directional derivatives with some exercises.